All right, so Charlie, can you please put your hand up? Charlie? Okay. Victor? Okay. Tom? Okay. Nico? Hi. Chris? Okay. Ray? Hi, Ray. Jerome? Derek? Okay. And Leland? Okay. And Poya. All right. So
we derived the formula for the gravitational potential energy and the escape velocity.
yeah, we derived the formula for the gravitational potential energy and the escape velocity. Let's move to this part of the worksheet number 5. These are all the type of questions you will come across during the test. This is a practice review for y'all. Let's start this point. Gravitational potential energy. Please read along with me. We have
gravitational potential energy.
So what should we write here? Nico, can you say me what should we write here? The gravitational potential energy value? Because you already have known what is this EP value. Okay, very good. Next point. However, okay, can y'all help me to derive this? What are the steps we follow to get this final value? We start from
MGH.
Okay, and then
G
is equal to GM divided by R squared.
And H is equal to R.
okay, and then we cancel R and R and we get the final EP value. And do you still have this doubt about the negative sign?
No.
Okay. However, please read. Please read.
G is not a constant, but rather depends on
the mass of the planet.
Please write also along with me. Mass and
resistance.
And radius. Okay. All right. And this small g is g m over r square, and just we are repeating. All right. Now try to read this statement. Whenever
we talk about gravitational potential energy, we have to use a reference point. At this reference point, we assign a gravitational potential energy of 0.
So when we are saying the word reference point, this is the point you decide. So normally when we try to draw the graph for R versus E, here is our origin O, and this point is our reference point where R is infinity, PE is 0, V is 0. So this is our reference point where your gravitational potential energy is 0 and you are coming in the satellite from that point towards Earth. Okay? This is the point we discussed yesterday, right? This graph. This is our reference point where PE, the gravitational potential energy, is 0. That is your reference point. Gravitational potential energy here is 0. And V is 0.
0.
Yeah? Okay. Jerome, can you please help us read this second statement and fill out the answer here?
Whenever we talk about gravitational potential energy, we have to
Right.
when determining the potential energy on a mass provided by the gravitational force generated by a second mass, we assign a 0 reference point when the distance between objects is.
Distance between the object is? Where is the object? Here is the Earth. Where is the object? If you see this graph, you are starting from this point. So where is the object? Where is the other satellite?
Infinity.
Infinity, yeah. The distance is infinite, yes. Okay, can you all please draw the graph by yourself? Try to draw this graph. This part. Try to do it. We have the PE here, the Earth here, R here, ready? Are you all ready?
Yes.
Yes.
Okay. This question, try to read and say me what you think about it. Is it possible for you all to do it or no? We have the mass This is the mass. And this is the distance. So that's R. 3.60 times 10 to the power of 7 meters. What is the GPE?
The change of rotation.
Is it easy? Can you all manage it?
We are calculating.
Okay, calculate, no problem. Victor, can you give me the answer for this question, Victor?
Still calculating.
Okay, all right.
6.37×10^-18。598×10^-4。要笑死我！-1.5.
Negative?
2.35 times 10 to the power of 10.
How, 10 to the power of 10 what?
Joules.
Okay. So, if you have this answer, it is correct. Now, the next question is a bit challenging. Are you all still working on this problem?
No, we finished.
Okay. So this part is little bit challenging. What is the total energy of the satellite in this planet? They are asking you the total energy. So you remember yesterday we did that kinetic energy plus potential energy initial, that is I is equal to the kinetic energy final plus the potential energy final. This was, and then I said you this is very important equation. Change in the kinetic energy is negative potential energy, and the gravitational potential energy, the gravitational potential energy is minus Z m 1 over Rf minus 1 over Ri. Yeah. So this and these equations are really important. And this question is asking us the total energy. And when we say total energy, it is the kinetic energy plus the potential energy of the system. So in this problem, you already have the potential energy here. You have the number here. This is the potential energy, but we need to find out the kinetic energy. We do not know the kinetic energy here. Once you have the Ke value, you can add both the energies and get the total energy. So can anybody say me, how can we find the kinetic energy here? Elan, can you please help us?
The kinetic energy is equal. The kinetic energy is equal 0.5 times the square of the velocity times the mass of the satellite.
Yeah. So what can you substitute the values? Because this is the kinetic energy that is correct. So that is half into this mass is the mass of the satellite. So this mass you have to take this value 2500 kg.
Why?
Sorry? So the mass here is 2500, that is correct. But what is the velocity? How I will find out?
10, 3 times 10 to the power of 3 meters per second.
How did you get that?
Square root gm divided by r.
Square root, if we find value of square root gm divided by r. So here my question is, will you consider the orbital velocity or will you consider the escape velocity?
Orbital velocity.
Orbital velocity. No escape velocity. Okay. So instead of writing, plugging in the numbers, you can write G m over what? Because it is the square, so you don't need the square root sign. Gm over? Give me the V value, please. Half into 2500 times G times M over R. What is the R value? This is the R value you have to use, the previous question. This is the R, 3.60 times 10 to the power of 7. And then you get the kinetic energy, which is how much?
Radius is not sweet.
Miss Rita, we should add the radius of the Earth because the question states that the satellite is 3.7 times 10 raised to the power of 7 above the Earth's surface.
Very good. You have to add the radius of the Earth here because this is just the altitude, the height. I have shown you the graph of altitude. So you have, this is just the height, you have to consider RE. Very good.
The final answer is 3.5 times 10 to the power of 10 joules.
The final answer, or is it just the kinetic energy?
the final answer.
Yeah, but
By the way, we need to-
but what is the kinetic energy?
the kinetic energy is 1.18 times 10 raised to the power of 10. This is kinetic energy.
Yeah, that's correct. So did everybody get this approximate value of 1.18 times 10 to the power of 10 joules? Did you all get this value?
Yes.
And then you add this value, the KE value, to your PE value here. Add it, but you negative sign. You have to take care of this negative sign.
Ms. Rina, when we calculate the total energy, do we need to consider the negative sign of the gravitational potential?
Now you think, if you consider the gravitational potential energy negative sign, or you don't have to consider, think. Because that negative that negative sign shows you that your value of the potential energy is below zero.
Yes.
Okay, so will you take into consideration that negative sign or no to find the total energy of the system?
We are not sure.
Because, okay, when you were in smaller classes, you did 10, I give you add, I say plus, add the two numbers, 10 plus minus 6. Or I will say minus 10 plus 6. You will do minus 4, right?
Yes.
That's just obvious. So because your potential energy is negative, you have to take into consideration. The value is negative. So you will write the total energy. I will say you the total energy here you will write. There's no place here. I'll just write it here. Okay. So ET is kinetic energy plus the potential energy. Add the two numbers 1.17 or 1.18 times 10 to the power of 10 plus minus 2.35 times 10 to the power of 10. You add, because this is a positive and a negative sign, the ultimate energy of the system is negative. You have to consider the negative sign because that's its energy below zero value.
Okay.
Now, if you are fine with this question, we can move forward. If you have some questions, please ask me.
Move forward.
Okay. Now this one, go to this question. Just that it's below that question. How much work is required to move 4,600 kg satellite from an orbital radius of this much meters to the radius of this much meters? So how we begin this problem, that our objective is to take one satellite, that this is the mass of that satellite, and you need to take that satellite from this radii to this radii. You have to pick it up, go up. So suppose this is the, sorry, you want to try by yourself?
What is the planet?
Okay. If the planet is not mentioned, And the question is saying how much work is required to move this much satellite from an orbital radius of this planet, sorry, orbital radius of this value to the radius of this value. Do you need to take into consideration the mass or no?
Yes.
Okay,
Yes.
and in this type of questions, you have to take Earth as the center point. And you want to try, or you should Miss Rena write the steps?
We want to try.
Okay, so just the important part is the work done. What do we mean by this work done? Can Victor say me how can we take into consideration this work? Work done is what?
Change.
Change in gravitational potential energy.
Very good. Change in the gravitational potential energy. So can Nico please say me what formula should I write to find out the change in the gravitational potential energy, that we have some energy initially and then some final energy. You solve first and then let me know. Okay, Nico?
Oh.
Miss Rena.
Yes, Poya?
Is the answer negative 7.6 times 10 to the power of 10 joules?
No. I will draw the figure for you that we have the earth here. Okay, this is the earth and this is the center of the earth. And our satellite, the weight of the satellite is 4,600 kg. This is the point where it is right now. Here the radius, you can write Ri is 1.8 times 10 to the power of 7 meters. And you want to raise this satellite from this particular point to a new point, a new radii, which is 4.2 times 10 to the power of 7 meters. So this is the final RF. So this is your point where the satellite is right now, and you want to take the satellite to this point from I point to F point. So you are doing some kind of work here to take the satellite from this point to this point, and work is delta gravitational potential energy, change in the gravitational potential energy. So you have to use the potential energy formula to get the difference between the two values.
Miss Rina, is the answer 7.6 times 10 to the power of 10 joules?
You are approximately there. Approximately. You are touching it, but it's not the exact answer. Maybe some calculation mistakes. So final minus initial. How much?
5.8.
9.8 times what?
5.8. No, not this. 5.8. 5.8 times 10 raised to the power of 10.
Yeah, that is correct. That is correct. That's approximately 5.7, or you can say 5.8. That's okay. 10 to the power of 10 joules. That is correct. So here, these are all the steps. And please look, you have to just specifically, you have to take into consideration the negative sign, because this is the final gravitational potential energy. This minus sign is there, this minus sign, because of the change, the delta change. Therefore, we have this minus sign here, this minus sign, because of the delta. Because of this delta, the change, we have the negative sign here. And this negative sign is because of the gravitational potential energy's negative status. So this negative and this negative turns to positive. So when you divert the equation, you have to write Ri minus Rf. Just take care of these three steps.
So the final answer should be negative, right?
Think, if you get negative, it is negative. If you get positive, it is positive.
Negative.
Did you get the negative answer?
Yeah, negative.
How?
Oh no.
No, because if you solve this part is positive, so you will not get the negative answer. If you solve this reciprocal relationship, this will be 4.2 times 10 to the power of 9 minus 1.8 times 10 to the power of 9 over 1.8 times 10 to the power of 9 times 4.2 times 10 to the power of 9. So if you subtract these two values, this will be 4 and this will be 3 minus 1, that is 2 times 10 to the power of 9 over 1.8 times 2.4.2.
The figure in the question is 1.8 times 10 raised to the power of 7, not 9.
Okay. Seven, seven, 7, 7. So this will be 7, 7, 7, and this 7 and this 7 will make 14. So this is just the fractional part. You have to multiply this z value, this m value, and this m value here. Are you okay with the numbers or still you have some confusion?
Okay.
So this part is the final answer. Poya, is your point about the negative value clear or still it is not clear?
It's clear. Because the 1.8 is in the denominator.
Yeah.
So it should be positive.
Okay. In this class, hello, in this class, who did not get this value? Put your hands up if you don't have this value. And if you have this value, it's okay. But if you don't have, we should find out why your value is not matching. Okay, let me check. Whose answer is not matching? Jerome, your answer is not matching? Whose answer is not matching? Okay, Nico and Island, right? Tom, okay, I'm sorry, Tom. So, can anybody help Nico and Tom to find out why the values are not matching? Can you please help? Just look at their work. Please help them. Anybody can move ahead and help. Chris can help Nico. And Derek, can you please help Tom? Please help him so that we can move forward. We are already out of time now. Okay. Just we can finish this problem and stop the class, no worries.